Let's say that somebody asked you, what's the best way to get from Rutgers University to Princeton? Is there one right answer to that question? In addition to all of the problems generally of evaluating generative QA questions, or generative AI generally, questions like these are hard to answer because there are many possible interpretations of the question, and some users might prefer some interpretations over others. If the person asking the question has a car, then you might say, get on Route 1 until you get to Washington. But if it's rush hour, you might say that they should take Route 27 south instead. If they didn't have a car, then taking New Jersey Transit to Princeton Junction and then taking the Dinky into campus is probably the best route. If you're really into biking, then the DNR towpath next to the canal is probably better. Now, you might say that all of this is ambiguity, and we've talked about ambiguous question answering elsewhere before, link in the description. The person asking this question should have been more explicit in what they were asking, remove the ambiguity, and provide the appropriate context to answer the question. And to a certain extent, that's true. You could rewrite each of these questions into a context-free version. This is similar to what we did for Canard, our dataset that rewrites conversational questions in context into standalone questions. But what's different about this is that the resolution of the ambiguity depends on the person asking the question. This can be even more extreme. Let's go back to that example that I started with. What if you're an undergrad at Rutgers who wants to go to grad school at Princeton? Then the answer to the question might be work on research, take advantage of a summer research program at Princeton, get good letters of recommendation, and perhaps even recommending particular Rutgers professors who already have collaborations with Princeton professors. So the question is, how could you, let alone a computer, know how to answer these kinds of questions? Ellen Voorhees probably put this best. Without any idea of who the questioner is and why he or she is asking the question, it is essentially impossible for a system to decide what level of detail in a response is appropriate. Presumably, an elementary school-aged child and a nuclear physicist should get different answers to at least some questions. So how would a system actually know who the user is? In a seminal paper from 2005, Teven et al. Viewed a user as a collection of documents. That's what defines what the user is. So if the system has access to a collection of papers that they've written, or an email corpus, or Reddit threads that they have participated in, this is certainly a coarse way of defining who a person is, but it's a start. And you can see how this could sometimes be effective. If you're an NLP researcher asking about translation, that's very different than a health researcher using that term. And again, different from, say, a computational geometer. And this kind of disambiguation will be implicit in your personal corpus. For the equations I'm about to show you, they don't assume that your corpus is part of the information retrieval collection. That makes sense if we're talking about your emails. So to do a search that's relevant for you, they adjust the IDF component of traditional IR frameworks. If you need a refresher on that, I have a link in the description to my lecture on TF-IDF. But the basic version is this. You have an IDF term in the equation. It's a way of handling words like the that appear in so many documents that it shouldn't really be viewed as important to a query. Teven et al. Don't build directly on TF-IDF, but rather on BM25, but the intuitions are the same. To turn this into math, if you have n equals 5,000 documents in your collection, and the appears in all of them, then when you plug it into this equation, you have big N equals 5,000 over N of little I equals 5,000. The log of 5,000 over 5,000 becomes 1, and log of 1 is 0, so that means that this term isn't important. So the idea is to use the importance signal to boost words that are important to a user. So let's look at the expanded equation from their paper. And so in addition to the previous N terms that were here before, we now have an R term that corresponds directly to how many times this appears in the user's collection. If there's no personalization, then all of that goes away and you're left with the normal IDF. But let's think about what happens with personalization. For concreteness, let's say that the word we're talking about appears 90 times in a corpus with 1,000 documents. That means that the IDF is just about 1. So let's plot this as a function of the number of documents that the personalized term is in. You'll notice that when it doesn't appear at all in your personalized corpus, you can actually get negative IDF. This is one of the quirks of BM25 and why I don't teach it in my class. In practice, you need to either turn this into a small epsilon or something like that. But you can see that when the word appears enough times in your personalization corpus, the weight goes up. First a little, then a lot. Again, I assume that the term appeared 90 times in your normal corpus. If it appeared more in the normal corpus, the curve shifts to the right. If less, shifts to the left. In other words, the more often it appears, the more the personalization matters. This is an old school technique, but you can see how this could be incorporated into newer methods. Many question answering systems are conditioned on retrieved documents. So you could pair a BM25 retrieval step with a Muppet model generator to create your answer a la RAG. But what about changing that generation procedure? You might want to tailor the response to target, for instance, the age of the user. If somebody with a physics PhD asks you, why is the sky blue, you don't want to talk about how light bounces off the air and some light bounces more than others. You should probably use more direct technical language and explain things in terms of wavelengths and Rayleigh scattering. This represents knowing something about the user. In this paper by Quarteroni, they specifically estimate the age and reading level of the user to generate the correct complexity of the answer. While they approach it as a filtering step to select the appropriate source documents, this could be incorporated into a constraint on the generative question answering step, a la RAG, like I mentioned before. I don't know of anyone that's done that yet. If you do, please leave it in the comments. But there are more dimensions that you might want to consider in personalizing your answer. In this EMLP paper that won the Best Paper Award, they attempted to figure out whether questions are situated or connected to a particular time or place. This was written right as vaccines were being rolled out for the coronavirus, and it's a great example. This is something that people really cared about, and it was different in just about every jurisdiction. Moreover, it changed really quickly. Suddenly a new vaccine was approved, and people wanted to know when that happened. This is a case where people needed the right information right away. There are many great aspects of this paper, including considering the longevity of a fact. The last World Cup champion changes every 4 years. Well, except in 1962 when Brazil won for a second time. Likewise, the President of the United States changes every 4 years, except when a president is re-elected, or resigns, or is re-elected 1,000 years later. This paper provides not just a data set for annotating how long an answer is valid, but also creates classifiers to detect when a question is situationally specific. When the classifier fires, they rewrite the question to be situationally specific, like we did with Canard. So where do we go from here? I think there are a couple of directions. First is that we have only scratched the surface of the possible amounts of personalization. We've talked about several important dimensions for personalization, but there are many more. How much meat is okay for me to eat has very different answers if you're pregnant, Jewish, or in a place with a listeria outbreak. And at the start of the video, we talked about how people can have idiosyncratic preferences about how they travel, the kinds of media they like, or their favorite sports team. These questions are handled effortlessly by most humans. If somebody in the great state of Iowa asks you on Monday morning, "Did you catch the game last night? How'd we do?" The answers that you would get are very different if you're in Almaty County in the northeast, Lee County, home to Keokuk, Iowa in the southeast, Fremont County in the southwest, or Lyon County in the northwest. And this is to say nothing about the personalization possible if you have access, say, to somebody's email, like we talked about from the 2005 paper. You can personalize quite a bit here. Google's Bard is an example of this. But at the moment, this is focused on specifically saying, hey, look for the answer in my email. And it doesn't use that information implicitly to generally figure out who you are. The bigger challenge would be to build representations of users that could infer the dimensions that warrant personalization. To be clear, many don't. The first human in space is always going to be Yuri Gagarin, no matter who asks the question. But the challenge is to learn what actually needs personalization, and this will likely require large amounts of data. Something like finding similar questions in different subreddits and seeing when they have dramatically different answers. And it would also require new representations beyond personalized retrieval, perhaps building a vector a la item response theory to encode dimensions that require personalization for particular people. Until we get to that, I'm not going to get the answer that I want to the question, how do we personalize QA? This is just one video from a course that I'm teaching. If you want to get the whole context, check out the course webpage, linked below. There you can find all of the videos in the right order. YouTube likes to show you older videos out of order, homeworks, exercises, and recommended readings. And if you want to help other people find videos like this, please be sure to like and subscribe to provide a big gradient to the algorithm.